And in the cell below, we started to write another function called shuffle and get stat. The function takes no input variables. It first creates a new table containing all the data from ends, but with the months column shuffled. You'll have to decide whether to replace the rows when sampling or not in order to shuffle the rows. Well, we know that replacing the rows allows rows to be picked multiple times, which isn't allowed in shuffling. So we should make sure that the with replacement is false, right? The function then returns the value of abs, diff, and delays applied to the shuffle table. We then have some code that you should complete to generate 200 simulated statistics using shuffle and get stat. Store them in an array, display the histogram. Okay, so we want, when we're sampling, because we want to shuffle the rows in the table ends, we're going to set with replacement false. So we can only pick each row once, and so we do. And then we're going to grab the months of those shuffled rows. So that's really just taking the month column and shuffling up the labels. And then we take our table ends, and we replace the month column with the shuffled months labels, call that shuffled ends table. And then we call our function that computes the test statistic on that table, returns it. We want to make an empty array to store our statistics. We want to do this for loop 200 times. And what are we going to do? We're going to run this function to get shuffle and get the statistic. And then we're going to put that statistic, new stat, on the end of our array. And after we've gone through this loop, we'll have 200 statistics. We want to put them into a table. And then we want to make a histogram out of that table. Where do we want the bins to start? At 0? Looks like we didn't tell you anything about where to put the bins, so let's just leave that off and just take the default. And so this can take a little bit of time. So while we're waiting for this to do its business, let's have a look at question 18. It says, looking at your histogram, but we don't have a histogram. That's okay. We've got the picture over here. Okay. So looking at your histogram, how large does the test statistic have to be for you to be very, very confident in rejecting the null hypothesis? Okay. Does it have to be -2? No way. It is to the left. It's pretty badly to the left of the histogram. So, but I don't think you can have an average flight delay of -2. So that's kind of bogus. 0.05. That's the cutoff value for, or this level of significance for a particular level, 5%. This is 1%, but those aren't relevant. What we want to do is find a value of the test statistic that's way outside of this range, right? And how about 3? If we had a test statistic of 3, how likely would that have been to have come out of these simulated statistics? Super unlikely, right? Because it's not even in the same table. So I would say if we have a test statistic of at least 3, an observed statistic of at least 3, we'd be very confident in rejecting the null hypothesis. And do you reject the null hypothesis? Well, our observed statistic was over 7. So yeah, it's totally not on this. It's like way over here, right? So we reject the null hypothesis, and we have to conclude then that the labels mattered, that they were that the months really have different distributions. So we're rejecting the null hypothesis. So I think it's 1. Okay. How much more do you have? 3 more. Okay, let's hustle a little bit. Okay, so in question 20, we have data on yearly landscaping expenses of a sample of 100 houses in the town of University Park, Maryland, where I live. The mean is 950. And the standard deviation of our sample is 150. Find a 95% confidence interval for the average amount spent on landscape. Okay, so here we don't have a table to sample from and bootstrap and resample and do all that great stuff. So instead, we'll use these values. And we know that if you were asked for a single number as your estimate of what the landscaping expenses would be, it would be 950. Okay, but we're asking for a range, and we've got a 95% confidence interval. 95% confidence interval for a normal distribution means that, remember that 95% of the values are within 2 standard deviations of the mean. So I'm going to subtract off 2 standard deviations to get to the left end. And how big is the standard deviation of the sample average? Well, it's the population standard deviation, which is 150. But then, and we're estimating that from just the standard deviation of our sample. But then we have to divide by the square root of the number of observations. There were 100 observations. So that's the left end of the confidence interval, and the right end, we just add 2 copies of the standard deviation for the sample average, which is standard deviation of the population divided by the square root of the number of observations. Okay, so we're 95% confident that the true number is between $920 and $980.